I'll be your moderator for the morning sessions. So I'm here to present our first invited speaker, Professor Angelo Montanari. So Angelo Montanari is full professor of computer science at the University of Udine, Italy, where he chairs the data science and automatic verification laboratory. He received the PhD in logic and computer science from University of Amsterdam in 1996 under the supervision of Johan van Benthem. He has published over 300 contributions in international journals, conferences, and handbook chapters. His main research interests include formal methods, artificial intelligence, and data science. He has made significant contributions to the fields of logic for time granularity, interval temporal logics, and timeline-based planning. He participated in many national and international projects. In particular, he is the scientific coordinator of the Interconnected Northeast Innovation Ecosystem, INEST. He has been the supervisor of more than 15 PhD students. And since the 1st of October, he will be the rector of University of Udine. And yeah, without further ado, please, I'll let Angelo Montanari speak. Thank you.
Thank you. Thanks. I'm very happy to be here. I would like to thank Alessandro and all these organization people. And as he said, now I'm currently living a double life. I'm still living my first life, which includes also what I'm going to do today, but I also started to live my new life, which consists of still a lot of problems, but of a different kind. So, okay, I'm happy to still be in the first life today. Okay, I'm going to present some work we are doing, we and the people which are mentioned there in the last few years, in which we try to pair an emerging formal method, which is monitoring. I'm coming from that area, so I feel the majority of you is from the other one, machine learning, and the machine learning guys are mainly Andrea Brunello and Nicola Saccomando, but I try to do my best today. And this work is a way of putting together monitoring and machine learning in a field which is quite relevant from the point of view of industry. When I read the title of the symposium, I thought that this was a very appropriate topic because we try to put together research for sure, but also application. As a matter of fact, we are currently within the project that was mentioned before, we are currently applying this framework in a couple of major industries in our area. I'm from Udine, northeast of Italy, and the industry are Danieli, steel, very big steel industry, and Electrolux, another big company. So we are trying to experiment on concrete, real data, the framework I'm going to present you. Okay, first of all, I try to introduce where I come from. I come from formal methods, and I think that all of you are familiar with them. Two main problems there are, in logical terms, satisfiability checking and model checking. The first one is a sort of sanity check that we have to do whenever we have a formal specification in logical terms, and we want to guarantee that it is actually satisfiable, it is consistent, there are no contradictory requirements in the specification. And then the model checking is the formal methods that can be used to ensure that the behavior of a model of the system against a specification of its expected property is correct. And the distinctive feature of these formal methods is that they are effective, as you know. And so in many critical contexts, they are actually highly desirable. But as we know, there are some criticalities in that. In particular, one, specifying in advance all the relevant properties that you want to check. And second, building a complete model of the system against which you have to check your requirement is often out of reach in real-world scenarios. So these techniques are fundamental. I still believe in them. If you want a small digression, there is this emerging interesting topic about the possibility of synthesize the specification from natural language description by using LLM. This is another direction. I will not talk about that today, but this is for sure something very interesting. This is not the case at the moment, because a hot topic, we started to work on that, is to provide some formal guarantee that the formal encoding of natural language specification is correct. And this is an open issue. Also, how can we try to establish that? Somehow, I feel that yesterday in some sense, we talk about that. Maybe today in the panel we can go again on this direction. But for the moment, classical approaches to consistency checking and model checking are still there, but with this relevant limitation. And the idea here is that we try to go on somehow to try to overcome, in some sense, this limitation. And to this end, we develop a framework that, one, it supports monitoring. And monitoring is a lightweight runtime verification techniques which does not require an explicit model of the system under consideration. This is a very important feature of monitoring. And then, second, we pair monitoring with a machine learning tool to automatically extend the set of property to monitor on the basis of historical trace data. So in this case, we do not assume to have a complete description, a complete set of properties we want to check, but we are open to the possibility to increase this set, to add further property on the basis of collected data sets. So this is a different way of using machine learning with respect to what we heard yesterday, because this is a sort of integration. It's on a pair with formal methods. Just an observation, I'm not saying that monitoring is going to replace consistency checking, model checking, but rather the idea is that you can do your usual stuff, consistency checking, model checking, and then you still need to monitor your system because you cannot be sure that your specifications were complete. So you must be able to check the actual behavior of your system and to be prepared to do something. And in particular, and this is the application domain, this technique, monitoring, is quite important in order to support these two fundamental tasks. We can define a failure as a deviation between the observed behavior of a system and the expected one. And by the expression early failure detection, we refer to the process of identifying potential issues or faults in a system before they escalate into major problems or a failure of the system. And as soon as you are able to detect them, the better. And such a proactive approach is useful not only for preventing catastrophic failure, but also to try to minimize downtime and thus reducing the maintenance cost. If you are not able to prevent the failure, the system has to be stopped, you have to do something, and then you have to restart the system. And this is very costly. And so the idea is that we should recognize as soon as possible them and try to do something that maybe can avoid halting the system, or at least to reduce the time of this downtime. And that's the idea. And this is something that when you talk with the industry is immediately recognized as an important and significant problem. Okay, so what I'm going to tell you today is a short account of 2+1 topics. I will spend most of the time talking about monitoring and this important notion of monitorability. If I have to say what is monitorability in a couple of words, the point is that not all properties are monitorable. So we have to identify which are the properties that we are able to monitor. I will be more precise in a moment. Then I will say a couple of words about the integration of monitoring with machine learning. How do we use machine learning to improve the system? And finally, and maybe this can be interesting, I will point out some current research and development topic, and some future possible extension of this work. So I'm going to talk about my own work, which is not standard in an invited talk, but I think that the framework is sufficiently general to be of interest for many people, and in particular, I will try to describe it. I will be very fast on the technical details, and I try to give you the general picture of these tasks. So first of all, I want to focus on monitoring. As I say before, monitoring is a runtime verification technique. Runtime means that you apply it during the functioning of the system, not in advance. And it allows to make a formal evaluation of the system by checking a finite prefix of its current execution. So you can imagine, as usual in this field, that the system goes on forever, and then you monitor it. You follow the behavior step by step. So at any time you have analyzed a finite prefix of the behavior of the system. And the idea is to be able to detect either failure or success. I will be more precise in a moment. And this condition of failure or success are expressed by means of a temporal logic formula. And the distinctive feature of monitoring is that your conclusion, your verdict, the verdict of a monitoring algorithm is irrevocable. So once a failure or a success is detected, all continuations of the execution of the system are guaranteed to be failures or successes. So you don't need to go on. You came to a final conclusion. Here, maybe you understand that not all properties are monitorable in this sense. So it's not surprising, because monitoring is asking for something very strong. On the analysis of a prefix, I must be able to derive some definitive conclusions. This is a picture, very high level, of how we can think of a monitor. We have a property, temporal logic formula. We have a system. And then in between, we have this monitor. The monitor observes the behavior of the system, the finite trace of its execution. And it, if possible, it comes to a conclusion, to a verdict, and possibly gives a feedback to the system and to outside. So the main steps, if we want to synthesize what is the behavior of monitoring, is the following. First, we want to check bad or good. I will be also on that a bit more precise in a moment. Bad or good behaviors of the system on the basis of the finite trace, which are specified by means of this temporal logic formula. How can we do that? So the property is specified by a temporal logic formula, but to make this process effective, we transform the formula into a monitor. And with this monitor, you may think of, in general, I will say something at the end of this talk about that point. You can think of the monitor as a finite state automaton, as a deterministic finite state automaton. So you follow the behavior of the system, and in the meantime, you are moving on your deterministic finite state automaton. Keep in mind that we are looking at finite prefixes. So the automaton is working on finite words. Even though the behavior of the system is an infinite trace, you always consider finite prefixes. So the automaton works on that kind of languages. And yeah, in principle, you can use the monitor both online, as I'm describing it now, but in principle, you can also analyze offline the behavior of the system, the traces of the system. For instance, if you have a failure traces, you can try to recognize the prefix that tell you which kind of problem has been encountered. Okay, monitor and monitorability. And we have, first of all, to distinguish between two kinds of monitorable properties, which are positively monitorable and negatively monitorable properties. And I give here two very simple examples. To the right, you have an example of a negatively monitorable property. And the property is the program never enters a deadlock. So you may think of the finite trace as a sequence of I, instruction, whatever instruction you want, and at a certain point you encounter a deadlock. And at that point you can conclude that your property has been violated. You don't need to follow the behavior of the system. You are done. In this case, we talk of negatively monitorable. We can talk about a violation of the property. The property that allow this kind of monitorability are typically safety property. And in that case, a finite prefix of a sequence, of an infinite sequence, suffices to establish that the system is not satisfying, is not able to satisfy the specific behavior of the system, is not able to satisfy the property. In this case, negatively monitorable. Classical example of positively monitorable property is the property the program terminates. Again, instruction, 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 instruction. At a certain point, you have termination. In that case, you are done. You don't need to go on, or you can replace termination with any property you expecting the system is going to realize. And in that case, you stop. And in this case, we talk about co-safety property. In this case, given a finite prefix of the sequence, infinite sequence, you are able to establish that the system actually satisfies the property. And you don't need to expect any time anymore. Okay, so these are the two kinds of property, positively and negatively. Positively, co-safety property, negatively, safety property. If you want, co-safety means existential property, safety means universal property. Okay, so I want to be a bit more precise about which kind of properties are monitorable in this sense. And I have to very briefly remind you, I think you are all familiar with that, linear temporal logic. So linear temporal logic is the logic of linear time. It has the usual stuff, propositional letter, negation, Boolean modalities, and then two modalities, temporal modalities, the next operator and the until operator. The next x phi says that at the next time point, tomorrow, the formula phi holds, and the until phi 1 is a binary modality, phi 1 until phi 2 says that there exists time point in the future where phi 2 holds, and from now until that point, not necessarily including that point, phi 1 holds. From this modality, as you know, we can define the eventually, sometimes in the future phi, and we can define globally, always in the future phi. Keep in mind these two derived modality because they will come into play in a moment. It is possible to add past modality to LTL. Basically, we add the mirror modalities. So you have next, tomorrow, you add yesterday, previous. You have until, phi until psi, phi 1 until phi 2, and you have phi 1 since phi 2, sometimes in the future phi 2, and since that point up to now, phi 1. And there is also here the possibility to define some derived modality once in the past, historically, always in the past, but also, and this is what I need in a moment, a weak formal yesterday. When you say yesterday tilde phi, you means not yesterday, not phi. Why this is important? Because while the future is unbounded, in the past you have 0 time point, you have an initial time point, and so in this way, when you use this weak form of yesterday, the formula is true even if you are in the first point. If there is no past point, this formula is trivially true. While in the case of the yesterday, the strong yesterday, if you are in the first time point, the strong yesterday can never be true, because there is not a previous point. This is a technicality, but this is useful to identify in a formula the initial starting point. Okay? Because you can say something like, weak yesterday false, and the only way to make this formula true is to be exactly at the beginning of time, because there is not a previous point. So this is the way in which one can use this, one possible use of this. Okay, now a bit of formalization. It is possible to identify a fragment of LTL, which is the so-called co-safety fragment. So such that all the properties that you can express in this fragment are positively monitorable, because they are co-safety property. And if you look at the syntax, it's not that surprising. You have the next, okay? And you have the two existential modalities, the future, sometimes in the future, and the until. The until is mixed up because it has existential but also universal part. But this is also part of the co-safety fragment. So if you write formulas in this fragment, you know that they are positively monitorable. For instance, P until Q is positively monitorable. There is a very nice result. This is a result by, if I remember well, Chang, a PhD student of Vardy, many years ago, that says that the very same fragment can be defined by means of formulas of the form F, sometimes in the future, and then the argument formula is a pure pass formula. So is a formula of this logic in which you only keep the pass modality. And if you think a bit, when you write the formula of this form, F of alpha, where alpha is a pure pass formula, this formula behaves in this way. Suppose that you start from the beginning of time, time zero, you go somewhere in the future with the F, and then your formula only talk about the past, which is very natural if you want to analyze prefixes of a trace. You go somewhere and then you look just at what happened up to that point. So you may think of using this formula to increase step by step the prefix until you get a point. And there is this formal result that states that these two fragments, the one of LTL and the other of LTL plus past, are equivalent, express the same things. Okay, so here you have an example. You can say something like F, sometimes in the future Q, and yesterday, so starting from the previous time point, if it exists, always P in the past. So F, PLTL is a canonical form for co-safety LTL. It's a very strong result. By the way, I didn't remind that, but if you add past to LTL, you do not increase the expressive power. So you can express the very same properties you can express in LTL, even though there is a difference. The difference is that in many cases you can be more succinct. So you can express the very same things, but in many cases by using shorter, more compact formulas. Okay? So this is for the co-safety. As for the safety is universal properties that you want to check if they are violated. And not surprisingly, here you have again the basic stuff, you have the next, and then you have the universal modalities, the G, and the release. Release is the negation of the until, is the universal counterpart of the until. So for example, you can write things like G, R, then next, G. If you read R as a request and G as a grant, you say whenever someone requests something in a couple of times, at least tomorrow or the day after tomorrow, the grant is given. And again, there is a canonical form for safety LTL, which is very similar to the previous one for co-safety. The only difference is that in that case you have G, the G modality, always in the future, and then the argument formula again is a pure past temporal formula. So safety and co-safety property can be expressed by means of this fragment, F of alpha, G of alpha. Is this all? Not really, because the class of monitorable LTL properties is larger than the union of safety and co-safety. I have here an example. I don't know if I can try to show it quickly because it's not difficult. This is a formula which is neither safety nor co-safety, but it is still monitorable. And the formula is a disjunction. The second disjunct is always in the future G, and the first one is an until, which says P or Q until R. And we can observe, first, if you take an infinite sequence of P, this infinite trace satisfies the formula. But no one of its prefixes is good, because if you stop at some time, you cannot conclude that it is satisfying. So this is not a co-safety property. Remember, you need to find a prefix such that, and so on and so forth. If you have an infinite sequence of Q, this does not satisfy the formula because you need sooner or later to realize R, but none of its prefix is bad because you are going on, you are keeping Q true, so you can wait for R in the future. So it is not a safety property. But everything R is a good prefix for the formula, provided that either P or Q or both holds up to this position. So you keep P or Q, at a certain point you get R. So this is a good prefix. You realize your formula. And if at a certain point you obtain that neither P, neither Q, nor R are true, this is a bad prefix. Because remember, you have to keep P or Q. At a certain point, you have neither P nor Q, so you need to have R. If R is not there, you can conclude that you are done. There is no possibility. So this is a bad prefix. So any finite prefix which is neither good nor bad can be extended to a good or a bad prefix. Okay? Any letter containing R, suppose that you are keep going, any set of proposition letters which contain R makes the prefix good, while a continuation when you have the appearance of this not P, not Q, not R makes the prefix bad. So this is a monitorable formula. It is not safety, it is not co-safety, but it is monitorable. Just to give you the confirmation, not all formulas are monitorable, as we expected. And a very simple example is the following one, which is a nice, a very common formula, because it's what is commonly called a reactivity property. Like every request is sooner or later granted. And what is the problem here? The problem is here in the universal quantification, every. Why? Because if a request has not been granted up to now, you cannot exclude that it will be granted later on. And if up to now all the requests have been granted, you cannot conclude that you are done, because there can be a future request that will not be granted. So this is a classical example of a property which is neither positively nor negatively monitorable. So what is important for us? First, we have to know that what we can expect to monitor must be a property which is monitorable. And then it would be nice to be able to identify monitorable fragments, and we did it. And also, and that's the step that links the first component, the monitor, to the second component, the machine learning, it would be nice to instruct your machine learning tool to learn only monitorable formulas. Okay? So this is monitoring. I started to look into monitoring some years ago, not that many. At the beginning, I was a bit We have some doubts about the effectiveness of these two, but actually it is very useful together with the classical ones. So again, I want to insist, I'm not proposing to replace them with this one, but to pair them with that one. Just to, again, a small digression, the very same situation is very important in planning. In planning, you want to check whether a plan exists that allows you to achieve a certain goal. You want to be able to build a plan, to generate a plan, but you cannot exclude that there will be some events in reality which was not taken into account when you built your plan. And how you can do to check that? You can monitor the behavior of your system. You can realize at a certain point that something unexpected happens that deviates from what you assume about the environment. So the idea of monitoring is very, very general and can be applied in a number of fields. So this is the reason why I started to look inside and to work on that. Nevertheless, there are some limitations which are similar to the one I mentioned at the very beginning, also in monitoring. First of all, the system we are going to consider, also the application system I mentioned at the beginning, have such a level of complexity that is really practically impossible to assume that an engineer, a system engineer, is able to identify and specify all the relevant properties to be monitored since the beginning. And moreover, even minor changes to the system can be introduced some unexpected bugs. So you must be able to keep into account also this one. Okay. And what to do, and this is the second step. The second step is how can we solve, or at least we can address this problem by pairing monitoring and learning. So the idea is that we can try to learn in an online, iterative fashion, new formulas to be monitored against the system. How? By analyzing traces, at the beginning at least, by analyzing traces, prefixes that lead to a failure event. So here is a very simple example. You have this time series with this variable y, which leads to a failure, the red sign, and then we try to learn formulas that recognize in advance situations that will lead to this problem. For instance, we want to detect this fact that the value of y is over a given threshold. At that time 7, we recognize that it is no more the case. Remember, this is a safety property, G, so we want to detect violation. And possibly we want to anticipate. We can recognize that not only when we are below 3, there will be problems, but also when we are below 5. And so we want to look at, clearly, I always say, if you look at the people, we can say that we start to die when we burn. So we want to anticipate, not too much. Okay, so we have to find the right place, we have to recognize the right pattern that lead to a failure and to distinguish them from the normal behavior. Okay, so this is not a trivial task. But as soon as you anticipate, the better, because you can, as I said before, you can do something and you can avoid, Okay, so given a trace, the idea of this component is to generate a formula that triggers only on the failing prefixes, not on the good part. So we must be able to distinguish the two components of the behavior of the system. And the idea here is that, okay, we start monitoring by identifying a set of initial properties, the obvious ones. To the limit, you can also assume that you start more or less with the empty set of properties, and then you start to learn. In the original framework, we distinguish between a warm-up offline phase and an online phase. In this warm-up phase, in a fully automatic fashion, the framework analyzes the known traces of the system that led to a failure. And then we extract from these traces new relevant properties with the goal of anticipating their identification. And during the online phase, when the system is at work, the framework monitors the system in real time, and if a failure occurs, it derives new relevant formulas. Hopefully, if the failures is of a kind of the failures we already detected, you anticipate it, but you cannot exclude that something new happens and something negative new happens, and then you have to refine the pool of formulas to be monitored. And just a couple of words, because I see that time's flying. Instead of using LTL, we use signal temporal logic, STL. I say a couple of words about STL, and you get the point, I think. And as the machine learning component, we use the genetic programming, genetic algorithms, because they have the useful flexibility and the possibility to constrain the form of the property that we want to learn. In particular, remember, I want to learn monitorable properties. So we can play with this algorithm to be able to constrain that. Couple of words about LTL, very quickly. LTL essentially is an extension of LTL, of the standard Boolean qualitative semantics of LTL, true or false, with some quantitative component. So for instance, the standard qualitative semantics allow you to establish whether a given signal satisfies or not a given formula, true or false. The quantitative component, here we have an example, allow you to assign a real valued measure to the satisfaction or to the violation that allow you to understand how much it is satisfied, how much it is violated. You can understand that with respect to threshold. If we must be above the threshold, it makes a difference. If you are just above the threshold, you are a lot above the threshold. And similarly, if you are below, just below the threshold, or a lot below the threshold. And in that case, this logic gives you this possibility to measure the robustness of your satisfaction or violation. And this is something very useful in the domain we are considering. So this is the reason why we use this in many applications, STL instead of LTL. But always what I say about LTL, safety fragment, co-safety fragment, the characterization in terms of F and G, pure pass formulas can be done in STL. The very same result can be achieved there. So you can think of what I say before in the framework of this language. And then we use the genetic programming component. And the idea here is that we receive a prefix of a failure trace. We receive a set of good traces in the training. And we want to generate a formula, which is an STL in the fragment of safety co-safety, that characterize this bad behavior. And here we essentially identify the individuals with the formulas, and each formula is represented by its syntax tree. You see one to the right. Here you have always in the future, main outermost operator. Then you have a since, and you have the two arguments, x greater than 3, y greater than 7. Then you can apply the classical the classical operators of genetic programming, mutation and crossover. Mutation, you can introduce some mutation in the trees. Crossover, you can exchange some components, some subtrees of the trees. And then we put, and this is where we exploit the characteristics of genetic algorithms, we put a threefold fitness function. So we have three different objectives. First, we want to measure, to evaluate, to count on the effectiveness of the formula phi in recognizing the augmented set of traces as failing ones. We want to avoid false positive, to recognize as bad behavior some behavior which is in the set of good traces. And we want to award early identification with respect to time. So as soon as we are able to identify, the better. And at the end of this process, taking into account these three goals, we get a formula which has the highest hypervolume from the Pareto front. And this is a formula of this fragment of STL. All right, here I think I have to skip. This is the framework. I will leave the slide so you can take a look, and I also have some references at the end. We have the warm-up framework, and we have the runtime framework to the right, and there is this, in blue, you see the component where we use the genetic programming component. Which are the distinctive features of this framework? We know, you know maybe that the very same problems has been addressed with purely machine learning techniques, neural networks of different kinds, or other solution that I will mention in a moment. While we propose this kind of approach, we see at least three main advantages. First, interpretability. The machine learning method, in our case, works on and produce formulae, which can be easily inspected by the system engineer. Second, we have this formal guarantee about monitorability, so the formula that we are going to produce in the learning phase are guaranteed to be monitorable, and this is done syntactically by playing with the grammar which is used to generate the computation tree we saw before. And finally, this is a very general framework. In principle, you can imagine to replace the monitoring component, for instance, by replacing LTL with STL or with any other possible logic. And you can imagine to replace the genetic programming algorithms with another component. But the general idea is still there. Okay, I think I have to go to the conclusion here. Is just to mention that there have been purely machine learning techniques which have been used, random forest, neural networks in various forms, support vector machine. But in that case, for this kind of application, we believe that the lack of interpretability is really a non-trivial problem. And there are various directions we are moving on. And here I mentioned some of them. Maybe I can try to say something here. The first one is that problems with the complexity of the monitor. Why? Because the monitor can be seen as a deterministic finite state automaton, but we start from a formula. So we have to translate the formula into an automaton, in general a non-deterministic automaton, then we have to transform the non-deterministic automaton into a deterministic one. And this may involve a double exponential increase of the complexity. So the point is that, is there possibility to make monitoring in a simpler way without the necessity of building an automaton? And actually, there are some cases in which this is possible. And this is the case of what has been called in the literature intentionally safe and intentionally co-safe formulas. This is a classification of formula which was introduced by Vardy some years ago. And we show very recently that you take this kind of formula, you can do monitoring without the need of building an automaton, but just by analyzing the trace. So you can do monitoring by trace checking. Clearly, there is one small problem. You have to recognize that a formula is intentionally safe or intentionally co-safe, and this costs a bit, but less than this double exponential complexity. This is a very recent result which works on the monitoring component. And then there are also other aspects which are more concerned with the old framework, and in particular the machine learning component. One is that, okay, we look at failure. Failure means a crash of the system at the end. But there are also other phenomena which are interesting. And we started to look at anomalies, which are the difference between failures and anomalies. Maybe anomalies are behavior which for a certain time deviate for the expected behavior, but later on they go back, or more or less go back. So you may have a drop of performance, but the system is going on. Or in some cases, you go back to the normal behavior. And so in advance, you don't know if you are encountering an anomaly or a potential failure. And also the way in which you model the anomaly may be a bit different from the way in which you monitor a failure. And so this is something we are looking into now. We also are thinking of diagnosis. Diagnosis is something different, because if you want to diagnose a problem, maybe you have to have some information about the model of the system. Remember that all these techniques do not make any assumption about the internal behavior of the system. You just observe the events which are happening during the behavior of the system. So this is purely observational. In the case of diagnosis, you want to give an account of why something bad happening, why some anomalies are emerging. You maybe have to add some knowledge about the model, but not too much, because if you have too much knowledge, you are going back to model checking. So you would like to do diagnosis with some information, some more information about the system, but not too much. And this is another aspect. About modularity, I just mentioned. So in this item, what we are doing is trying to replace or thinking of possible replacement of the genetic algorithms with other solution. And unsupervised and self-supervised learning techniques is what can we do if we have no a priori a set of failure traces? Can we do something also in that cases? This is the case for anomalies. There are no bad traces in that cases. So we can do something, we can learn something also in this case, and supervised learning, as we did in our framework up to now, is not sufficient, so we are looking to unsupervised or self-supervised learning technique, which can maybe help us. Okay, I think I'm just in time, and I hope to have been able to give you the flavor of this work. There is at the end some references, some are general references, and the last ones are the main references to our work. The main venue where we present this framework is the ICHCAI last year. We have an improvement in ICAI this year, where we introduce the use of GPU to make the genetic algorithms more efficient. And there is also this paper about automatons monitoring we just submitted. Thank you for your attention. Thank you.
Thank you so much. Yeah, we have time for question. Anybody wants to start?
Thanks for the talk. So you talked about interpretability. So of course, I mean, compared to, I don't know, interpret neurons on a neural network is way easier to interpret for an expert, for a person, temporal logic formula. But I wonder what kind of formulas are output on your real experience? I mean, because it is not even easy if a system learn by itself, I don't know, 70 parameter linear temporal logic formula. So are they also concise, the formula that it learns, and they are easily understandable by the experts, or they tend to be complex themselves to be interpreted?
Yeah, that's a point. I skipped the part about the experimentation that we did, and we take some public data sets. One in particular is about problems with hard disks. And in that case, we recognize that there are formulas which allow us to recognize in advance some problems, and they are relatively simple. I would say they are formulas where you have this threshold, and essentially you are able to anticipate the proper threshold. We are still working on real case. These are public data sets. They are more or less real, I would say, but we are working on these real data sets from the companies, and we will see whether the formula we are going to detect are. But I expect them to be maybe big disjuncture of simple formulas. I do not expect such a level of nesting of modalities, for instance. This is something that we do not expect. So in some sense, I would say, yes, they are, up to now, formulas which are readable from someone who knows the meaning of these thresholds. That's the experience up to now.
Next question.
Well, first of all, thank you for the talk, and I guess thank you for sending some love to the industry people as well in the audience. It's always appreciated. So I have a couple of questions. I'll make them both and then I'll shut up. So the first one, you gave some intuition about the learning process, and in the example you showed, you were, as I understand, learning universal formulas. You started with a failure, and then you were learning those that you call universal formulas. My question is, what's the intuition if we wanted to learn existential formulas, and in your experience, if there is any difference between the two in performance or in I don't know, some effectiveness of the process, of the learning process in the two cases. And the second question is more of a curiosity, I guess. So what's the current state of the art for the tools that are available? You mentioned some collaboration with industries. What are the tools available now to apply this kind of techniques in a real world scenario?
Yeah, thank you.
Thank you.
Yeah, it is not surprising that actually the examples are of negatively monitorable formulas, because usually this is the kind of formula you are interested in. You want to guarantee the good behavior of the system, and you want to detect violation of some properties. The situation is the classical one. If you know, just one, Mann and Prueli wrote a series of books about verification, and they started with the safety book. The second book was safety, and at the end they have some draft of the book about liveness properties. So it is also in that case, it is easier, but it is also more natural in this framework to consider safety formulas. And so, because you are interested in the good behavior of the system and you want to detect bad events. So we have not so much experimental results about the other case, even though in principle they are the same. So if you look, the kind of formulas are basically the same. You just have the G or the F, but essentially it's something that you have to guarantee at each time point, or you are looking for a time point. So in terms of the machinery, there are not so many differences. But in the real domain, most of the properties are these kinds. As for your first question, the framework is completely implemented, and I can say in my experience, these two companies, I don't say which one of the two, have their own tool for doing something similar, but they decided not to use that one and to try to experiment our one. So it is at a level of development that allow it to be experimented, validated on real-world data. Now the problem is the way in which they collect data, which is not, they are not immediately usable and useful. So we are in the work of cleaning the data in such a way we are able to apply the system, but the system is there. So it's very, I'm a theoretical guy, and my collaborators are more, not more, they work a lot also on that part, and so we are ready to check the system, not only on public data set, but also on real data. And there is an issue of intellectual property, but this is another stuff.
Any other questions?
Yeah.
Please.
Thank you very much for your talk. It was very interesting. And I think in particular, seems like a very interesting topic for industry. From my perspective, I can really see tools like monitoring being used for debugging the traces. You know, sometimes as a developer, we debug when something goes wrong. I mean, I work with databases, and we usually try to understand why the query running for long, right? And we go to the logs and try to trace down all the steps that the optimizer took to produce maybe a bad plan. So to have a monitor that can track the logs from the beginning, and then fire when there is a query that was not a cross product, and at the end the query optimizer produced the cross product plan, and it will send me a message saying, you know, something is really wrong something went really wrong in the system. So I find it very interesting. So as far as these monitors go, I was wondering how configurable the construction is. In a sense that if I want to build a monitor, do I need to start every time from scratch, or is there a way to reuse some pieces that I used for developing a different monitor? And my second question is also related to configurability. You mentioned that there is an issue of translating the formula into an automaton. And I suppose you were talking about the sort of classical state diagram automaton. Have you considered the structured way of representing automaton, going back to algebraic automaton, where you can have a cascade of automatons that basically where each component represents a certain functionality that could potentially be reused?
Okay, very, very nice question, both of them. I have no time to answer all of them, but I want to say that you touched two very, very important points. As for the first one, I skip a bit that point, but when you recognize a new property and you want to add it to the pool, you have to guarantee consistency, because it is not for free. So you have to do something there. And also the issue that you raise is that, okay, I have already a monitor for this set of property. I add a new one, it is okay, it is consistent, but can I refine the previous monitor instead of rebuilding it from scratch? We didn't work on that. So you can assume that you rebuild it from scratch. But in principle, yes, it could be nice to. And the other stuff is something I'm working on my theoretical part of the mind, because we are working on Cascade with not all these guys, but with Luca Giatti and other people. And this is important because it is easier to monitor when you write formulas in the past fragment of LTL. But we know that there is this open issue about the complexity of turning a formula of LTL into a pure past one, even with this G and F. And in that case, the idea of using cascade of automata may be useful. We have some preliminary results. Also, Alessandro is very familiar with that, maybe also you. And yeah, this is a long-term goal we are working on, and maybe it could be useful also here. So yes, for the moment, we're talking about generic standard automata, but it makes sense. And maybe in that case, some form of compositionality could come into play. No, but that's a really nice topic, but it's, yeah. It's
Thank
there.
you.
It's there, yeah.
Thank you.
Okay, I think we don't have. Oh, you want? Okay.
Not a question, like a meta question. I mean, I think we have plenty of material to discuss for the panel. From
Yeah.
this talk. Like I have 10 questions just myself.
Okay, thank you again.
Okay, thank you very much.